Thank you so much for that, and again, thank you so much for inviting me to present today, and a huge apologies for not being able to make it down to Denny today. I've just got so many competing meetings at the moment and activities, I just wasn't able to travel down. But hopefully I think my presentation can Kimberly asked me today to present specifically on impacts on crop yields and also on some of our engineered enhanced efficiency fertilisers. And it's quite interesting. So when we first discussed that as a topic for today, that was before the fuel crisis and the fact that urea has nearly doubled in price. So yeah, I think that could be quite topical. I've also got a little funny story on biochar, and this goes back to about 10 years on our own farm. So we have cattle and custard apples, and I actually had a bolter bag, about a cubic metre of Russell Burnett's poultry litter char sitting in the cattle yards, and overnight our cattle broke through a barbed wire fence and consumed a whole cubic metre of biochar. So yeah, that was destined for the custard apples, and never actually ended up making it on the custard apples. But yeah, just to show that it's a highly desirable product. What I'm going to do now is go straight to crop yield. So I'm specifically talking about impacts on crop productivity, and I'm going to try and break this down in the next couple of slides. So I think Russell mentioned that there are 6,000 papers on biochar and sort of agronomy. That's actually a bit of an underestimate, Russell. It's probably up around 20,000 now, and overall there's 57,000 papers on biochar-related topics, everything from use in asphalt, remediating metal-contaminated soil, right through to its origins around terra preta and improvements to soil carbon and soil carbon processes. But just focusing on yield, some of the early work, there was a meta-analysis done by Jeffrey back in 2011, and I think there were maybe then about 15 research papers in 2011 looking at biochar impact on yield. So his paper showed that on average, adding raw biochar at that stage gave improvements on average of around about 10% to crop productivity. It's also got to be noted though, that there are many cases and scenarios where there are no improvements in crop productivity, and we'll go into some of those a bit later on. And another paper that I'm going to focus on is quite a recent one in 2020 by Yi, where he's shown that that benefits from biochar range anywhere sort of from 15% up to about 30%. This graph is a little bit scary, but I'm going to go through it in a little bit of detail. So what we're looking at here is this meta-analysis by Yi and Marta Kamps and Johannes Lehmann and others, where they've had a look at this meta-analysis of studies all over the world, and we can see that there were 5 studies on the map there originated from Australia, but many studies from all over the world, and particularly Europe and China contributed quite significantly to this work. And here they're comparing application of biochar versus a non-fertilised control. And we need to be, and the next slide I'm going to show is the impact of biochar compared to a fertilised control. So in this study, it uses a whole stack of statistical approaches to basically pull out data from 150 odd research papers into one relatively useful graph that I think helps us to understand the role of biochar in soil. And again, noting that by far the majority of these studies that contributed to this particular slide are the application of raw biochar, so unmodified biochars. And we'll talk a little bit about modified or engineered biochars later, but these studies are mostly from raw biochars. And if we look at the mean effect size from 150 odd study papers, we're seeing that the benefits are around about 30% overall benefit yield. And what we can do is we can break it down into different categories. So we can have a look at impacts on crops. So here we had a look at sunflower and canola, and the benefit was maybe 10%, but there were also some negative effects. So that the width of that line shows the range of effects, and right through to a very heavy nutrient requirement crop like maize, where we often will see doubling in yield. We have a look at the feedstock that the biochars are made out of, and this is broken down into 3 different categories, even though now there are many, many more categories of biochars. But here they broke it down into cereal residue, ligneous material, basically wood chip type feedstock or green waste, and also paper mill residue. The cereal straws by far and away gave the greatest impact on crop productivity. We look at the HTT, the highest production temperature of the biochars. And quite interestingly, while the high temperature biochars, that are those with 400 to 700 degrees, gave a positive benefit, it appears to be that the lower temperature biochars tend to give a greater benefit to productivity overall. We have a look at the soil properties that it's been added to. And what's quite interesting is some of these clay soils, which might be the oxysols that Russell Burnett spoke about in the Amazon, those really highly weathered clays, there were some very significant benefits. The loam soils that tend to be a greater productivity, lesser benefit, and some of the sandy soils, for example, the work in Western Australia on the tenosols and the arena soils, again, gives greater benefit. So we're starting to get some idea here of the types of biochar properties and the types of soil properties where you likely get your biggest bang for your buck. We look at some of the other soil properties like cation exchange. Those with over 200 millimoles per kilogram, less of an effect. Soils with a lower cation exchange, biochar has a greater effect. This was very significant, nearly 150 or 1.5 times the benefit over the control. Organic carbon in soil is another really strong indicator. Soils with high organic carbon, i.e. these loamy soils, tend to have less of an effect. Soils with a lower organic carbon tend to have a higher effect. And interestingly as well, pH of soil is quite important. So soils with a neutral or alkaline pH have lesser effect. Soils that are acidic have a stronger effect. And one of the key reasons here for the pH effect is that the biochars tend to be alkaline in nature after their production. Even though we've seen biochars ranging from pH 6, but many of them are up around pH 8 or 9 or even 10. And they've got a liming capacity, some of them of between 10 and 30% that of ag lime. So some of these pH effects are purely due to their acid neutralising effects. I'm going to skip a few of these other factors and just go down here to biochar rates, so the dose, tonnes per hectare. It's not a huge effect in this particular scenario of where they've added sort of 5 tonnes or 20 tonnes per hectare. There's quite a bit of variability with biochar rate. But what's important here is where the biochar is added with nitrogen fertiliser, and we can see that when there's nitrogen added into the system, biochar tends to have a much greater effect than in a non-fertilised system. This particular slide now is essentially the same study, but where we've got fertilised control. So basically, biochar, with and without the use of inorganic fertiliser and organic fertiliser, over the conventionally fertilised control. What's very interesting to note here is that depending on the study type, the effect of biochar is less. So to me, that indicates immediately that a lot of the effects that we're seeing with some of these biochars is either it's fertiliser effect of the biochar per se, so the nutrients that the biochar carries that come through from the feedstock. So for example, Russell's poultry litter biochar, it's got 4% phosphorus in it. It's only half that of single super. So it's a very, very strong phosphorus fertiliser. It's got some nitrogen, it's got lots of available calcium in it. So there are nutrient effects there. But when you compare it against a fertiliser control, the effect is a little bit less. Some of the things that stand out again, though, are its role in soils with cation exchange capacity. So the fertiliser effect is probably diminished a little bit in soils that in this particular, actually no, there's not that much difference in the role of cation exchange, but it's just an important factor. But again, soils that have got low organic carbon, we saw a strong biochar effect, and again this pH effect, where you've got alkaline and neutral pH, not much of effect, or nil effect of biochar compared to the control. But in these acid soils, we are definitely seeing some effects of biochar. So in a nutshell, I think we've got now a pretty strong understanding of where biochar is going to have its greatest impact in soil, and this is raw biochar. And also now a lot of the science and a lot of the engineering is going into what's known as engineered biochars. And the second part of my talk really is going to focus on these biochar-based fertilisers. But there's also been a lot of work now around other types of modification of biochar. So I view biochar really as a platform material. So you've got this porous structure, lots of macro and micro pores in it, generally having large surface area, often hundreds of cubic meters per gram of biochar. And it actually makes a great platform material for putting things into, including biology, but chemistry in particular as well. Fertiliser obviously is a bit of a hot topic, and there's a lot of research on what's known as enhanced efficiency fertilisers and how they're used in agriculture. So I'm just going to go through a bit of a nitrogen cycle here. Many of you will have seen this type of slide before, but just to reiterate what we're trying to do here. So the majority of nitrogen fertiliser used in broadacre scenarios is added as urea. We've got enhanced efficiency fertilisers that slow down the release of urea from the pellet into soil. So that's one type of enhanced efficiency fertiliser. Then we've got some biological fertilisers. Basically, they're adding biological inhibitors or microbial toxins with the fertiliser. And we've got this other one called a urease inhibitor. So while urea might then dissolve into soil, it will stay as urea for longer, which means that there's less pathway for it to be lost to the system. So urea itself hydrolyzes to ammonium or ammonia. Ammonia, in particular in alkaline soils, can volatilize. In acid soils, it tends to be less volatile, and it will stay as its ion of ammonium. Ammonium then nitrifies, a bacterial process, to nitrate. So Russell mentioned that plants can take up both ammonium and also nitrate. Both are effective end fertilisers, but it does impact the form of nitrogen that might be in the plant then before it's converted into amino acids and proteins, for example. The problem is once we get to nitrate, in some farming systems, in particular in wetter farming systems, in higher rainfall systems, in irrigated systems, we can lose a lot of our nitrogen either through leaching nitrate, which is highly soluble and quite mobile in soils, because it doesn't stick to the cation exchange, because it itself is a cation. and we can also lose it through denitrification. So again, a biological process that produces dinitrogen, or N2, which is in the atmosphere, but on the way you can also produce nitrous oxide, which is a pretty potent greenhouse gas. But I'm going to focus right up this end here around this slow release fertiliser. So the fundamental concept of a controlled release fertiliser is to synchronise nitrogen supply, so the amount of nitrogen that's in soil, with the plant demand. So we add urea into soil or other nitrogen fertiliser, conventional nitrogen fertilisers. We've got a whole stack of nitrogen in the soil when the plant's small, or even before it's germinated, when the nitrogen's not needed. And what we're hoping for is that nitrogen hangs around in the soil long enough for when the plants actually need it. The problem is we've now got a period of days to potentially weeks where we've got some significant lost pathways. So denitrification or volatilisation of ammonia can occur in that period. So with controlled release fertiliser, what we're aiming to do is synchronise, and that's a blue line, synchronise the supply of nitrogen in the soil with the demand of the crop. So the problem with the existing controlled release fertilisers is for major crops like wheat, we can use these polymer-coated fertilisers. We're adding up to 10 kilos of plastic per hectare. So that itself can be problematic. So these coatings range from sort of 1 to 5% of the total fertiliser weight, and the thicker the coating, generally the slower the release of urea from that product. There are products that are typically either 45-day or 90 days, but also some of these controlled release fertilisers have got what's known as a 360-day release curve. Probably not that applicable to many sort of conventional cropping systems, but in sugarcane, for example, where in northern New South Wales it's a 2-year cropping cycle, having nitrogen available for the entire 2-year period is actually quite valuable. And these polymers, quite a range of plastics that are used, and polyethylene tends to be the principal one. So it's a big market. I presented some of this data at the last NSW conference, but the polymer-coated market now is worth $3.5 billion, or is estimated to be worth about $3.5 billion US globally. Interestingly, the enhanced efficiency fertiliser market is worth $7.2 billion and is projected to grow to $14 billion by 2032. Asia Pacific dominates the market and is driven by countries like China and India that are adopting sustainable farming practices, and they're particularly interested in more enhanced efficiency nitrogen fertilisers, both for production purposes, but also for meeting their country's greenhouse gas requirements. And there are major producers of these products. Interestingly, the EU has banned, or will have banned, most of these polymer coats by 2028. And part of that restriction is that they need to degrade by 90% within 2 years after their, 4 years, after their application. And the whole purpose of that new legislation, those new policy, is to reduce microplastic pollution. And we've all seen media articles in the last 12 months around PFAS, around microplastics, around macroplastics in agricultural soil, and how they might impact human health, value of produce, etc. So I think that's a great way to go. I guess, do we see a solution here? And for those in the biochar industry, the answer is absolutely yes. So this is an older product. We designed this probably 10 years ago, and I think Russell was involved in some of this manufacture, where we combined urea with biochar and then pelletized it. Sorry, I'll go back. And this particular product contained maybe 5 or 6% total nitrogen in the system. So rather than relying on controlled release fertiliser based on plastic. We're now relying on this porous structure. You can see here on the slide on the right an electron micrograph that Stephen Joseph did for me. We can see that porous structure of biochar being filled up with urea. The white stuff is urea, and that's going to slowly leach out of the biochar into the soil and act as a slow-release fertiliser. We've also done a lot of work around gaseous emissions from soil, and this is the meta-analysis that we published in the latest edition of Biochar for Environmental Management. This piece of work has been very, very well cited. In dryland cropping systems, when biochar is added with nitrogen fertiliser, we're seeing about getting close to a halving of emissions of nitrous oxide, which is quite significant. So not only does it lower the greenhouse gas footprint of that particular fertiliser, it means that there's more nitrogen available to the crop for productivity. In dryland cropping systems, there doesn't tend to be a huge impact on methane. There were some increases, some decreases in methane emissions, but it generally didn't have a major effect on methane in dryland systems. However, in paddy systems, there's very, very strong evidence, and there's been some great papers written about this, around how biochar can lower emissions of methane in that paddy system, and at the same time lower emissions of nitrous oxide. So I think there are some great opportunities to use biochar in conjunction with traditional fertiliser regimes in both dryland and paddy systems where gaseous emissions or greenhouse gas emissions are an issue. So how are biochar-based nitrogen fertilisers made? So we call these BBNFs. And there's a nice paper there in a great journal called Biochar, published in 2022, where we talk about a different range of mechanisms of making biochar. There are microwave methods where we're actually microwaving biomass with nitrogen fertiliser. You've got some physical mixing methods, which was our original product that you could see there that Russell supplied, where basically biochar was mixed with urea and then pelletised. You've got coatings, so a bit like the polymer coat. You can also coat urea or other fertilisers with biochar. You've got these more high-tech techniques where you're actually reacting now the nitrogen with some of the surface functional groups, and that's obviously a far more technical process. And you've got this infiltration method as well, where you might soak biochar in liquid urea, for example, or there's some other techniques. A process that New South Wales DPIRD is currently commercialising is based on a similar method to this, and I'll just mention that a bit later on as well. And what we have is a whole range of release curves, remembering that what our goal here is to slowly allow that nitrogen to come out of that product. So we're matching supply with demand. And there have been lots of different studies with lots of different techniques, but some of these studies are showing that we're releasing about half of the nitrogen from these fertiliser products at about day 40, which is really quite useful for the majority of our particular cropping scenarios. And we've based a lot of our new product manufacture on that particular release curve. Here's just an example of that particular product being used as a fertiliser in sugarcane. And this goes back to the question of rates, and Kimberly specifically asked me to talk about how much biochar is added to soil. And I think Russell summed it up quite nicely. It really depends on what you're trying to do. So we've now got a really strong understanding of some of the properties of biochar, the properties of soil, what you're trying to amend. In this particular case, the amount of biochar that's being added is not going to have a huge impact on your soil carbon content. We're adding biochar as a nitrogen fertiliser. So in this particular scenario, we're adding about 800 kilos of biochar-based product per hectare, but we're adding that as a nitrogen fertiliser. So there's actually no technique in the world that will measure the change in carbon content of adding 800 kilos of this product that had a much smaller carbon content. So it really comes down to the purpose of what you're trying to achieve. What we've shown from that particular trial is that the slow-release pellet released not a huge amount, but maybe 30 or 40% less nitrous oxide from that sugarcane farming system compared to its matched nitrogen rate with urea. This is another great example that of some of the work that's being done in the soil CRC. So on the left-hand side, you can see a fairly typical calcareous soil based on carbonate and shells. The key issue with a lot of these carbonate soils, one of the key constraints is high pH. So that particular site, I think it's got a pH of about 8.8. And at that pH, the phosphorus ties up very quickly. So you add a phosphorus fertiliser into that particular system and it's bound up as insoluble calcium phosphate almost as soon as you put it into that farming system. So inevitably, your crops tend to be phosphorus limited. We designed for the soil CRC and also Nigel Wilhelm at PIRSA a biochar product that actually acts as a slow-release phosphorus fertiliser. So it's now an acidic biochar where we've impregnated with phosphorus fertiliser, and we've got Nigel's team at Sardi or PIRSA was very excited with some of the results that they're seeing. So on the left you can see a typical phosphorus application, and on the right-hand side the matched P content as the biochar in this engineered biochar product. So some really quite exciting opportunities there to modify biochars for specific purposes. And we've got this range of outcomes from these biochar based products. So we can modify the pH of soil, we can modify the pH around the fertiliser granule. We can increase organic carbon in soil, but at the doses that the biochar is being added, it's quite minimal. There are opportunities to improve soil structure, water retention, and also microbial activity, as I think Russell has mentioned previously. But definitely with these biochar-based fertilisers, what we're seeing is enhanced ammonium absorption in soil. We've got evidence for lower nitrate leaching. We've got evidence for lower nitrogen loss from the system. And when you're paying $1,500 a tonne for urea, which works out at about $3,000 a tonne for nitrogen as N, we really want to see as much of that end up in the crop as possible, or at least remain in the soil as possible. And we've got evidence for improved yield and improved nitrogen use efficiency. So there's another meta-analysis. Sorry to bring these meta-analysis out, but we've got some great data. Again, Johannes Lehmann's team evaluated over 150 articles looking at biochar-based fertilisers compared to matched inorganic fertiliser. And the mean effect was a 10% improvement in productivity. And they go through various factors. Interestingly here, pH didn't have a great effect, but some of the biggest effects were related to the crop itself. So maize, again, being a crop like sugarcane that uses a lot of nitrogen, tended to have the greatest effect, whereas some of the other crops that have a lower nitrogen demand, the impact was less significant. I can share that study with anyone that's interested to have a copy of that work. So I think there's a huge opportunity here for utilising biochar as a substrate material for making these controlled release nitrogen and phosphorus fertilisers. And there's no toxic compounds and no plastic. I'm raising the question, can the biochar industry be part of this $15 billion industry over the next 5 to 10 years? And I think probably one of the most rapid ways to get adoption of broadacre biochar is through its development as a purpose-made product for delivery of nitrogen and phosphorus. Most farms, I would say the majority of farms, will use fertiliser of some sort, and I think this will be a great way to get biochar into agricultural systems. And I mentioned before that our organisation is currently working with a couple of industry opportunities to look at commercialising both biochars for nitrogen delivery, but also engineered biochars for addressing soil constraints like subsoil acidicity and acidity as well. I haven't really spoken about any of the carbon work that we're doing. I think I mentioned before that our 2006 field trial has resulted in lots of PhD projects and lots of papers and a really strong understanding of how biochar interacts with soil minerals to enhance carbon sequestration in farming systems. But yeah, thank you so much for your time. I'll stop sharing my screen. I think I've stopped sharing the screen and we're back to the room.
Thanks, Lucas.
I don't audio. Oh, yeah, I can hear the room again.
Perfect. Does anyone have any questions for Lucas while he's here? Yeah? Did you hear that, Lucas?
Sorry. Well, could you repeat that, please?
So the question was, how many tonnes of plastics did you say were per tonne of coated fertiliser put out? Can you repeat that statistic, please?
Okay, so the polymer-coated fertilisers tend to have between 1 and 4% of their total weight as plastic. So on an average application, you're adding between 4 and 10 kilos of plastic per hectare. That's roughly the rate. That said, that they absolutely do what the label says they do. You know, they are controlled release. There is strong evidence that they result in enhanced nitrogen use efficiency, and they lower greenhouse gas emissions. However, there is that catch in that currently the products that are available are adding plastic into farming systems.
Yeah, thank you. He just said that's disgusting. Were there any other questions for Lucas? Roger?
The DPIRD process, can you just explain that a bit more, Lucas, and the timeline for that technology or that IP?
The IP sitting at the moment, I can't explain the process in more detail at the moment. We are hoping to go out to tender to commercialise that for availability, for commercial scale availability by the end of the year. So we're just gathering all of the data and information on the product at the moment and working with some commercialisation people to scale up or to look at scaling up the IP. Apologies, I can't give more information on that product.
Excellent. Thanks, Lucas. We really appreciate your time. And I'm not sure if we have any other questions. Can we send them through to you?
Absolutely. I need to apologise. I've got another meeting to attend this afternoon. But if people want to email me or if they want to go through you, Kimberly, I'm more than happy to send any of those research papers through or answer any questions more specifically.